I'd now like to welcome Jonas Korndörfer. He's a PhD student in the HPC group at the University of Basel. Are you able to share your screen? And we're looking forward to hearing your presentation.
Okay. Hello, can you hear me?
Yep, certainly can.
Okay. Thank you, Tom. I will share the recording I made here. So just let's see. Is it looking good for you? Is it a full screen or something?
Yep, that's full screen. That's
okay. Good. So share computer sound. Okay, so I'll play it. Hello everyone, my name is Jonas Korndörfer and I'm here today to present to you LB4OMP, a load balancing library for OpenMP. Now, just a brief outline. I will start by talking a little bit about our motivation to create the library, the history of LB4OMP from where it comes from, then the library itself, which scheduling techniques it contains, which performance measurement features it contains, and how to use it. Then we'll have a look at some performance analysis that we conducted with LB4OMP, and finally some take-home messages. It's important to highlight that this project is partially funded by the Swiss National Science Foundation and by the project MLS, Multi-Level Scheduling in Large-Scale High-Performance Computers. On the right, you can also see some pictures of the team involved in this work, which is composed by Professor Florina Charba, the head of the group, Ali Mohammed, Ahmed El-Lemi, and myself. As for our motivation, well, load imbalance is a well-known performance degradation factor. It lowers the performance of applications, it causes the waste of resources and energy, and it can increase the waiting times in job queues, which will affect a lot of people in supercomputers nowadays. And furthermore, there is a huge amount of literature and research that proposed load balancing methods that have never been really implemented in any library and that are not available to anyone to simply use them and try to achieve a higher performance with them in their own application. So the lack of an implementation for such scheduling techniques and load balancing methods in general hinders the research for novel methods, since a comparison with what was previously proposed is not possible. And furthermore, it also may hinder the performance that is unachievable with what is currently available. Now a little bit about from where LB4OMP come from. So in 2018, we started our first efforts to implement some extra scheduling techniques to the GNU OpenMP runtime library, and this work was published at IWOMP. And with this work, we had some interesting results, achieving some nice performance and higher performance than the standard scheduling techniques. So we decided to approach the LLVM OpenMP runtime library, since it is more compatible with different distributions such as the GNU and Intel. And then we also explored this runtime library and we implemented one more scheduling technique. And at this point, we realized that LLVM was a good target, and we decided to expand our work by gathering as much as we could from the literature and implementing everything we could in the LLVM OpenMP runtime library once again. And that was a poster published at Supercomputing. And that's actually a very early version of LB4OMP. And then we arrived to today with LB4OMP that comprises some performance measurement features and the scheduling techniques. And we kindly like to see it as a Swiss Army knife of load balancing for OpenMP. In a nutshell, LB4OMP is a load balancing library for OpenMP. It bridges the gap between the state of the art of the literature about load balancing and the state of the practice of load balancing multi-threaded applications. It's based on the LLVM OpenMP runtime library, and it comprises 9 dynamic and non-adaptive self-scheduling techniques and 8 dynamic and adaptive self-scheduling techniques. And it also contains some performance measurement features. And LB4OMP is available on GitHub. It's open source, and everyone is welcome to try it. Now, which scheduling techniques are available in LB4OMP? It contains the standard static scheduling technique. It contains the 9 dynamic and non-adaptive self-scheduling techniques, which are the ones in the screen. And it contains 8 dynamic and adaptive self-scheduling techniques. It's important to highlight here that this is the first time dynamic and adaptive self-scheduling techniques have been implemented to OpenMP, and we will see later on the results are pretty interesting. And they are very important since they are the only ones that are capable of collecting information about the execution of previous chunks of iterations during the execution of an application. And by doing so, they can change the amount of iterations that each thread will receive during the execution. The following are the performance measurement features that were implemented in LB4OMP. The first one is about collecting the execution time of each thread in executing the loop. So it prints the values in CSV file format that prints the loop occurrency, which is basically a counter that registers how many times the same loop was executed, and that's mainly important for time-stepping applications, for instance, that execute the same loop many times. Then it prints the location, which indicates the function name and the line of code where you can find the respective loop, the number of iterations of the loop, the thread ID, and the respective execution time. Then we also allow the collection of the parallel execution time of the loop, which also prints the values in CSV. And then we implemented the functionality that registers every scheduling round, or more specifically, every chunk of iterations that was scheduled to every thread for every scheduling round. And this also prints the values in CSV. It prints again the location. It prints the lower bound and the upper bound. So in OpenMP, what happens is you have a central queue of iterations, and each thread identifies or knows which part of this queue it's supposed to execute by knowing its lower and upper bound. So we register this also, and then we register the chunk size or the amount of iterations that each thread received, and the thread that received this amount of iterations. It's important to highlight that this functionality can create really large files depending on the amount of iterations of the target loop. It can grow really, really quick. And finally, we have the profiling functionality. This is a functionality that works slightly different than the others. We will see soon. And it was developed mainly to facilitate the usage of other scheduling techniques that require profiling information. So it collects the mean iteration execution time and the standard deviation of the iterations of a respective loop. The usage of LB4OMP is pretty straightforward, and the first thing one has to do is to check if the target loops already contain the schedule runtime clause. If that's the case, you don't even have to recompile the application. However, you have to make sure that the loops you want to use the scheduling technique in LB4OMP are using the schedule runtime clause. The second thing, you have to link LB4OMP with your application, and to do that, you can add the path to the compiled LB4OMP to the environment variable LD library path. Finally, to select a scheduling technique, it works in the same way as the standard way. You can export the environment variable OMP schedule and define the scheduling technique and the chunk size. And in the current version of LB4OMP, we also expect a variable called KMP CPU speed, which is expecting the clock frequency of the target machine, and that's used for some timing functions that are of lower overhead. To use the performance measurement features and to configure them, it's done also through environment variables. To collect each thread and each parallel loop execution time, you have to provide the environment variable KMP time loop. And by doing so, it already activates the functionality, and you have to provide a path and a file where the data will be stored. To collect each scheduling round, you have to export the environment variable KMP print chunks and just activate it. So put 1 on it. And you have also to once again provide the KMP time loops with the path where you want to store this data. Finally, to use the profiling technique, you have to export the OMP schedule and choose profiling. And you also have to export another environment variable that is KMP profile data that is expecting also a path where the profiling will be stored. For our performance evaluation, we approached an application called Sphinx. It's a smoothed particle hydrodynamic code that is used in astrophysics for astrophysics simulations such as the collision of stars. It's a time stepping code, so we executed 20 time steps of the simulation, and each has 1 million iterations. The loops that we modified, that we added a scheduled runtime to them, were loop L0, which is a find neighbors operation, so it basically just identifies which particles are close to each other, and L1, which performs some math to calculate gravity, which is how each particle interacts with each other. We executed this application in 3 node types, so type A, B, and C. And we always executed the application 5 times on each node. The metrics that we evaluate, first we evaluate the parallel execution time of the application as a whole, but we also look at the exclusive execution time of each loop. And by having this information of the execution time of each loop, we can calculate how much performance is lost by executing the whole application with a single scheduling technique. So since we have the different times for every loop, we can see which is the best scheduling technique for each loop. LB4OMP and Sphinx were compiled with Intel, and the threads were configured with OMP place scores and OMP proc bind close. Here we have our first result for Sphinx executing on node type A. On the x-axis, you can see the scheduling techniques, and on the y-axis, you see the parallel execution time. You can see that there are different colors for the bars, and these are identifying from which loop these measurements come from. So in light green is representing loop L0. In dark green, it's representing loop L1, which is actually the most time-consuming loop of Sphinx. And in dark blue is the time outside of the loops. So basically, anything that was not measured by or was not influenced by the scheduling techniques. The background of the plot identifies from where the techniques come from, let's say like this. So in white background, you have the OpenMP standard scheduling techniques. In gray background, you have trapezoid self-scheduling, which was a technique that was already implemented in the LLVM OpenMP runtime library. And in green background, you have the techniques implemented in LB4OMP. You probably notice also the pink background, which is showing and highlighting the performance, the achievable performance with the best combination of scheduling techniques. We also have some red rectangles around some of the bars. In this case, both are on the FSC bar. And these rectangles are highlighting which was the best scheduling technique for a given loop. We can see that the best scheduling technique is a combination of techniques. In this case, it is twice FSC. And it's important to highlight that the percentages shown on top of the bars represent how much performance is lost by executing the application with a single technique. And here we can see that the best combination of scheduling techniques, or in this case only FSC, achieved up to around 13% higher performance than the best standard, which in this case was guided self-scheduling. And we can also see that the adaptive techniques, for instance, MAF, also outperformed the GSS by up to 9.5, 9.6%. So that's a very impressive result, since the adaptive techniques tend to cause slightly higher overhead, but at the same time they were more capable of balancing the load and by doing so achieving higher performance than GSS. Now here we have the results for Sphinx executing on node type B. The plots are configured in the same way as the previous plot. And here we can notice that the best is indeed a combination of different scheduling techniques per loop. In this case, FSC and MAF together compose best. We should also notice that FSC is not an adaptive scheduling technique, and it was not able to achieve the same high performance as we saw in the previous plot. So in this case, for this system, FSC ended up achieving 23% lower performance than the best combination. And we should also highlight that the adaptive techniques were able to maintain high performance between the previous node type and this node type. Even AF was still able to beat GSS and to outperformance GSS by up to 0.7%. Finally, we have the results for Sphinx on node type C. Here we can see that the best combination is once again two different scheduling techniques, one for each loop. And it is FSC and MAF again. However, it's important to highlight that now FSC, in this case FSC was once again achieving very high performance and achieving basically the same performance as the best combination. Here we can see that best outperformed the best standard by up to 12 or almost 13%. And we should also highlight once again that the adaptive techniques, or in this case MAF, outperformed also the standard ones by up to 10%. Now some take-home messages. First of all, LB4OMP bridges the gap between what is in the literature and what is actually implemented and being used for load balancing multi-threaded applications. It contains 14 additional to the OpenMP standard scheduling techniques, and it is a first and necessary step for the implementation of an auto-tuning or an automatic load balancing approach for OpenMP. By looking at the results, we can see that in most cases best is a combination of different scheduling techniques. However, we understand that it's quite impractical to find out which is the correct combination, since the amount of experiments is really huge. For that, the dynamic and adaptive self-scheduling techniques are a quite promising alternative to reach a performance that is comparable to best, or that's close to best, since they are more capable of adapting to different systems and maybe different workloads. Now, what we are going to do next, we are going to work on these techniques to patch and upstream them to the official LLVM repository. And we also are already working on an automatic approach for OpenMP for achieving the performance of best. I would like to welcome everyone to check out our GitHub and check out LB4OMP, and maybe you can even find out that your application can achieve a higher performance. Now I'm here open for questions.
That's great. Thank you very much, Jonas. That was really interesting. I'm very pleased to hear that you are working to contribute some of your findings and scheduling approaches into LLVM runtimes for OpenMP. So that's great.
Yes.
There's a couple of questions come in. The first was from Mats Bråsen, who says, what is taking time in the loops with poor dynamic scheduling? Was it poor memory location or scheduling overhead or something else?
Yeah, so yeah, I saw the question before. It's kind of a tricky question. How can I say? So if you can see poor memory location as part of a scheduling overhead. Also, if you take, for instance, self-scheduling, that is SS, it will give a chunk of one iteration for each thread, for each scheduling round. So the threads are just consuming, and these iterations are going everywhere. So you always have a higher amount of cache misses and all of this. So that is, how can I say, it's not simply saying it is a problem of memory or just a scheduling overhead. One thing is for sure, if you have to execute more scheduling rounds, so if you have to request work more times, then you have a higher scheduling overhead, but it also creates more memory problems, so locality problems. Yeah, I don't know if that's clear.
Thanks. I think another question that might be related is from Oliver Marsden, who says, how does your approaches behave with first touch initialization of arrays on multi-socket systems?
To be honest, I also see this one. I am not really sure if I understand the question.
So I think it's related to if you start moving tasks around between the NUMA domains, how do you make sure that you take the memory with you, or do you schedule the tasks where the memory is located?
Sorry, yeah, the scheduling techniques don't really take care of this. You basically they basically just calculate a chunk of iterations, and the threads will request, and they will give this chunk of iterations to the thread. But if it's located on a separated socket, or if it's migrating from one socket to another, this is not controlled.
Okay, that's brilliant. There's one more question in the Q&A, but I think I'll ask if you can take that in reply in text.
Yes,
that's all right. We're at a short break now, just to give everybody a quick break and step away from the screen, maybe make a quick drink or something. So we'll be back at 2:30, which is just in a couple of minutes now for the next talk. See you then. Thanks, Jonas.
Yeah. Oh, okay. Thank you.